If you ever meet a black hole, relax. It's the last thing you'll ever meet. Inside a black hole, you'll finally have time for everything. Because time stops caring. What happens inside a black hole? It's one of the most terrifying and fascinating questions in all of physics. A place where the laws of reality break, where time slows to nothing, and where everything, even light, disappears forever. To understand what happens inside, we have to start from the outside. A black hole begins with a collapse. A massive star, many times heavier than our sun, runs out of fuel. Its nuclear fire dies, and gravity, unstoppable, patient, and absolute, takes over. The star collapses inward, crushing matter beyond comprehension, until all that remains is a singularity, a point with infinite density and zero volume. Around that singularity forms the event horizon, the boundary of no return. Once something crosses it, there is no coming back. Not for a spaceship, not for light, not even for information. To an outside observer, an object falling toward a black hole seems to slow down. As it approaches the event horizon, time itself appears to freeze. The object fades, red shifted by gravity, until it disappears. But from the object's own point of view, something very different happens. Time doesn't stop. It continues normally. The traveler crosses the horizon without noticing anything special. But once inside, all paths, even those that used to lead out, now lead inward. Space and time have switched roles. There is no turning back. The pull becomes absolute. The curvature of space grows so extreme that no known force can resist it. The traveler is stretched, atom by atom, in a process called spaghettification. First the feet, then the torso, then the head. Gravity's difference between top and bottom tears you apart. Eventually, even your atoms are ripped into subatomic particles, and then information itself seems to vanish. But according to Einstein's equations, the story doesn't end there. Inside the event horizon, space-time curves infinitely toward the singularity. Every moment in your future leads there. No matter which direction you move, forward in time means closer to the singularity. There is no escape. However, quantum physics tells us something very different. It refuses to accept the idea of infinite density or information loss. According to quantum theory, information can never be destroyed. It can only be transformed. That creates one of the greatest paradoxes in science. If information falls into a black hole and can never escape, how does the universe keep its books balanced? This is called the black hole information paradox, and it's been haunting physicists for decades. Stephen Hawking once showed that black holes aren't entirely black. They emit faint radiation, now known as Hawking radiation. It arises from quantum effects near the event horizon. Over vast timescales far longer than the age of the universe, this radiation slowly drains a black hole's mass until it evaporates completely. So, if a black hole disappears, what happens to the information that fell inside? Is it lost forever, breaking the laws of physics? Or is it somehow encoded in the radiation, scrambled beyond recognition, but never truly gone? Some theories suggest the information remains on the event horizon itself, a two-dimensional hologram, storing everything that ever fell in. This is the holographic principle, the idea that our entire three-dimensional universe might, in fact, be a projection of data written on a cosmic surface. Others believe that the singularity might not be the end at all, but a bridge. A wormhole, perhaps, connecting to another universe or another region of space-time. If so, what we call a black hole here could be a white hole somewhere else, a place where matter and energy emerge instead of being swallowed. These ideas are speculative, but they show just how much we don't understand about reality. Einstein's general relativity describes gravity perfectly on a cosmic scale. while quantum mechanics rules the microscopic world. But inside a black hole, both theories collapse. Neither can explain what truly happens at the singularity. To solve that mystery, we would need a unified theory, a theory of everything, one that merges relativity and quantum physics into a single framework. String theory, loop quantum gravity, and other approaches try to do this, but none are complete. And so, for now, the interior of a black hole remains the ultimate unknown, a place where time ends, space folds, and physics itself surrenders. If you could somehow survive the journey, what would you see? At first, you'd watch the universe speed up. Stars would age, galaxies would fade, and time outside would rush by faster and faster. The rest of the universe would appear to end before you reach the center. Then, silence. No light, no motion, only gravity pulling you toward an end that never truly arrives, because at the singularity, the very concept of arrival loses meaning. Perhaps what happens inside a black hole isn't something the human mind can fully imagine. It's not a place, it's an equation that no longer makes sense, a paradox built into the fabric of existence. And yet, black holes may also hold the key to everything. If we can understand them, we may finally understand why time exists, why space has structure, and why the universe itself began in a singularity, the Big Bang. Because, in a way, the beginning and the end are mirrors. The universe was born from a singularity, and inside a black hole, another one may already be waiting.